In this video, we're going to go over the concept of the yields in OneStep and yields relations, which are useful because they give us a good way to define the operation of a finite state machine, particularly acceptance conditions, without even having to ever draw down a finite state machine. We can do it very formally using some mathematical notation. What you'll need to remember is the definition of deterministic finite state machines, and also what we mean by configurations of the machine, which I'll actually recap at the start of this video. So remember that when we are moving through a finite state machine, if we are sitting in a particular state, that is all of the information that we have about its history. It doesn't matter how many different states we went through to get to that state, that is all of the history information that we have. So that, combined with what symbols we still have to read from the input string, completely determine what the future of that finite state machine's operation is. So we can consider that the future of any particular finite state machine is going to be some function of its current state and what input it still has to process. We call that a configuration. So formally, a configuration of a finite state machine is a pair of a state and something that can be made using the input alphabet. So in this case, some string made in the alphabet. We can see then that we can specify the start of a machine easily with an initial configuration, which is obviously the start state, because that's what the state that we always start our finite state machines in, and whatever the input to that finite state machine is, because it hasn't processed any input. So to go over the concept of a configuration and moving between configurations a little bit more, let's use a concrete example. So let's consider this machine here, which has start state Q0, and let's consider the string ABB. The start configuration, as we said, so the initial configuration, is just the start state and the string. And we can see that because this is a deterministic finite state machine, we've only got one option. Well, the only thing that we can do with this particular input is transition over to this state Q1. So the configuration that will follow directly from that will be Q1, and at the point that we're in here, we've consumed the A from the string, so the remaining string is here. Now we can see that it wouldn't have mattered if we'd followed an A and then a B and then an A and then a B and then an A and then a B, however many times we wanted, if we eventually followed this transition here and had a B left on as input to read. So this pair completely defines the future behavior. And we can see that we've gone from one configuration and followed over to arrive in a second configuration. And this is what we'll be talking about when we talk about the yields relationship. So we're going to first talk about this yields in OneStep relation. So remember, a relation is just something that takes pairs from a set. So in this case, we're going to consider the set of all configurations. And the yields in OneStep relation is going to relate pairs in this particular direction if we can go from the first configuration to the second configuration in one step in the particular finite state machine M. So this little subscript to this yield symbol here means with respect to that machine. So here's the formal definition, but you can look at that a little bit more in your own time. But essentially, yields in OneStep means that we can go from a configuration of a particular state and an input to another and relate it to another state and an input if we can make one step in the machine to go between those two configurations. So before we had the configuration Q0 ABB, we can say that that does yield in OneStep Q1 BB because we can follow that transition. But we won't say that Q0 ABB yields in OneStep, say Q2 epsilon, because it clearly doesn't. There isn't one step that we can follow in this machine from this particular configuration to this one. So that's all the yields in OneStep means. It relates configurations, one configuration, to another configuration within the set of all configurations if you can move from the first configuration to the second configuration in that machine. So you'll notice that for deterministic finite state machines, there will only be one possible pair for any particular thing, but any particular configuration, because we always only have one option to move. Now that we have that yields in one step relation, which we've defined here, we can consider what it means to yield in two steps. So we follow that two steps. So we'll have one configuration, which I might call C0, and we can say that that yields in one step C1. So we can move with one step in the machine to get to C1. Now if I can get to C2, for instance, from C1 as another thing, then C0 will be related by yields in one step with C1, and C1 will be related with yields in one step with C2. But we can see that we can think of this as being able to yield in two steps straight from C0 to C2. So it'd be nice to have a bigger relation which simply relates all of the configurations that we can get to in any number of steps from a particular relationship. And you can see here that this maps very similar to our concept of transitivity that we had before. So because C0 is related to C1 and C1 is related to C2, then if we had the transitive closure of the yields in one step relation, then in the yields in any number of steps relation would have to relate C0 and C2, and also C0 and anything future in this chain that we've got here. So we take the transitive closure of yields in one step and we end up with a relationship that says yields in one or more steps. We'll also define the weird idea of yields in no steps to consider what would happen if we didn't go anywhere. And obviously, if we don't go anywhere from a particular configuration, the machine just stays in that configuration. So yields in 0 steps is basically saying C0 is related to C0. So if we take the reflexive and transitive closure of yields in one step, we end up with something that relates every configuration back to itself and also relates any pair of configurations to each other if it is possible to get from one configuration to another configuration, say Cn, using any number of yields in one step bounces. So basically, we say that it is possible using this machine to get from this configuration to this configuration. So that's what this yields general relationship says. Now you can see that that means that if we have any pair of configurations related by yields, then it is possible to move from one configuration to another in that machine. And that will be useful for defining the acceptance conditions, which I'll do on the next slide. So now that we have this yields relation that says that if I have any two configurations related by yields, that it is possible to go from the first configuration to the last configuration, we can define accepting configurations, which are simply a pair of a state and the empty string as input, with Q being in an accepting state and pairs of some state and input with Q not being in the accepting set of states. We can define that as our accepting configurations. And we know that we have an initial configuration for any particular string. So, a deterministic finite state machine accepts if and only if the start configuration is related to an accepting configuration by the yields operation. And because only one possible path through the finite state machine, one possible step can be taken at each particular point given any particular input for a deterministic finite state machine, we know that there won't be multiple pairs that we have related for a particular state and the empty string for any particular given input. So we know that if there is no such relation between the initial configuration and some accepting configuration, then there has to be a relation between the initial configuration and some configuration with no more input remaining, where the state is in this set of non-accepting states. So what we've gotten from this is a way to look at how relations and transitive reflexive closures and things like that can actually be useful in defining things like computation. And we've seen how we can define the operation of a deterministic finite state machine, particularly acceptance and rejection, formally without ever writing down a finite state machine or going through the steps, just by discussing this yields in OneStep and yields relations.